In this video, we'll be testing hypotheses by comparing means. Just like with hypothesis testing for a single mean, Ho will represent our null hypothesis, and Ha will represent the alternate hypothesis. However, unlike hypothesis testing for a single mean, when two means are compared, the null hypothesis must be expressed as a difference of 0. One way to compare means is by conducting a two-sample t-test. Here are some assumptions and conditions for conducting a two-sample t-test. Independence. The data for each group must be collected independently and at random. Groups must also be independent of each other. The normal population assumption. We should check the assumption that both group populations have an underlying normal distribution. Randomization. Is the data from a random sample or randomized experiment? 10% condition. This condition is only checked for small populations or very large samples. The nearly normal condition must be checked for both groups. Let's explore some of the concepts related to comparing means with an example. A recent newspaper article reported the average number of doctor's visits per year for smokers and non-smokers in their 20s. The 95% confidence interval for the mean for smokers minus the mean for non-smokers was given as lower bound 1.5, upper bound 3.0. The lower and upper bounds for this confidence interval are both positive numbers. What do these values indicate? Because the endpoints of the confidence interval are both positive values, we can conclude that the number of doctor's visits paid by smokers exceeds the number of doctor's visits paid by non-smokers. Note that this confidence interval does not contain 0. What can you conclude from this? Because the interval does not contain 0, it appears as though the possibility of no significant difference between the two groups is unlikely. The interval implies a significant difference between the groups. If we assign a 99% level of confidence to this problem, what is the corresponding alpha level? 0.01 or 1%. Now let's conduct a hypothesis test of two means with the following example. An educational research organization was interested in finding out whether there was a significant difference in the grade point averages of students who had been enrolled in a voluntary pre-kindergarten program prior to attending public school compared with those students who had not. The GPAs of 50 randomly selected graduating high school seniors who had attended VPK were analyzed. The mean for this group was 3.1, and the standard deviation was 0.09. A random selection of GPAs from 50 graduating seniors who had not attended VPK yielded a mean of 3.08 and a standard deviation of 0.08. All students had attended public school throughout their academic career. Test an appropriate hypothesis at alpha of 5% and state your conclusion. Assume all assumptions and conditions have been met. First, we need to set up our null and alternate hypothesis. Our null hypothesis is that the mean for VPK students minus the mean for no VPK is equal to 0. In other words, that there's no significant difference between the groups. Our alternate hypothesis is that the mean for VPK students minus the mean for students who did not attend VPK is different than or not equal to 0. Now that we've established our null and alternate hypotheses, we need to find the standard error. When working with two means, the formula for the standard error is the standard error for the first mean minus the second mean is equal to the square root of our standard deviation squared for group 1 divided by our sample size for that same group plus standard deviation squared for our second group divided by the sample size for that same group. In our case, the standard error for the difference of means 1 and 2 can be found by taking 0.09, raising it to the second power, dividing it by our sample size of 50, and adding this to our standard deviation for group 2, 0.08, raised to the second power, squared, divided by the sample size of 50. This gives us a standard error of 0.17. Next, we need to find the observed difference between the GPAs. This is found by taking the difference of the means. 3.1 minus 3.08 equals 0.02. Next, we'll find our value for t, and that is given by 0.02 divided by 0.17. If you use this method of calculation, you'll also need, when you get your result of 0.1176, to move your decimal one place to the right. This will yield a t-value of 1.176. Now that we've identified our t-score, we can use either a t-table or graphing calculator technology to calculate the corresponding probability. And from there, we'll state our conclusion. If you're using a graphing calculator, you'll type in the following commands. Second, distribution, normal CDF. For your lower bound, you'll type the t-score, 1.176. Our upper bound will be just some value off the curve, 100. Press enter, and that will give you a p-value of 0.1197. And actually it goes on 9797. So let's go ahead and round that last digit up to an 8. So 0.1198, or if we move 2 decimals to the right, 11.98%. This is our p-value. Before we state our conclusion, I want to point out that at the beginning, our hypothesis test was our null hypothesis is the mean of VPK students minus the mean of no VPK students is equal to 0, whereas the alternate hypothesis was the mean for VPK students minus the mean for students who didn't attend VPK being different or other than 0. So when we get our p-value of 0.1198, we need to take into consideration that a not equal to test is what we call a two-tailed test. 0.1198 would be representative of the probability in just one tail. In order to get the p-value for a two-tailed test, we simply multiply this value, 0.1198, by 2. This gives us a p-value for our two-tailed test of 0.2396, or approximately 23.96%. Our final concluding statement is, the probability of 24.96% is greater than our alpha of 5%. Therefore, we failed to reject the null hypothesis. The sample evidence do not support the claim that there is a significant difference between the GPAs of students who attended VPK compared with those who did not. We can also conduct a two-sample t-test using a graphing calculator and the following commands. Stat, test. Option 4, two-sample t-test. From here, we'll put in our mean for our first group, 3.1, our standard deviation for the first group, which was 0.09, our sample size for our first group, which was 50. Then we'll put in our sample size for our second group. Our mean for our second group, which was 3.08, our standard deviation for our second group, which is 0.08, and our sample size for our second group, which was also 50. Once you enter these values, you'll be asked to select either a not equals to, a less than, or a greater than test. Because we're looking to see whether there's a significant difference, we want the not equals to or two-tailed test. You'll be asked whether to select pooled or not pooled, and you want to select 0 for this. We do not wish to have a pooled test. Finally, you'll press calculate. And your result will be t equals 1.17 with a p-value of 0.2431, or we can represent that as 24.31%. Now you might notice that these values vary slightly from the ones that we calculated by hand. That's to be expected as we're using the technology, so there will be some minor differences. I'll leave this as a decimal since that's how your calculator displays it. Anyway, there's some information on conducting hypothesis testing for two means, as well as evaluating a confidence interval for two means.